Welcome back. This is our third and last video on stochastic calculus and continuous time methods. Now we're going to talk about solving stochastic differential equations. A forbidding title, but actually an interesting and fairly simple idea. You've done this in discrete time. In discrete time, we started with a stochastic difference equation, the AR1, and you know how to solve the AR1, meaning express today's x in terms of the long distant past and all the sequence of shocks. That's just the antiderivative, if you will, of this. That's the differential form. That's, if you will, the integral form. Our job is to learn how to do exactly that kind of operation with the kind of diffusion processes that we've been talking about. So let's start with the simplest one, the stochastic integral. We originally defined dz as the difference of the z process. Now we want to go back and do the corresponding integral of the differential that we took the first time around. So if you have zt and you want to go back to the level, why don't we just say that the level of z is the integral of all the changes? That's what we do in discrete time. In discrete time, the level of z is just the sum of all the changes. So the level of z in continuous time is the integral of all the changes. Now, what does integral dzt mean? What meaning can we attach to that natural notation? Well, it just means add up all the little changes. Integral dzt means let's add up the first change from 0 to delta, the second change from 2 delta to 1 delta, all the way up to the last change, and then make those deltas smaller and smaller and smaller. So the meaning of a stochastic integral of an expression of the form integral dzt is just add up all the little changes. And when you add up all the little changes, what do you get back but the last term minus the first term? Zt minus z0 is the sum of all the little changes. I should warn you, there's a lot of math under this. This is a different definition of integral than what you're used to from calculus. In calculus, the kind of integral you want to write, the way you would anti-differentiate, is you have integrals with dt's on them. And until today, that's the kinds of integrals you've always seen. The meaning of that integral is the area under the curve chopped up into little dt's. But that's not going to work for us here, because our curve is not differentiable. It's always yanging up and down. Therefore, we use this notation, dzt, and the idea add up all the changes, not the conventional notation, because we don't have a smooth function that we can take the area under a curve with. But that shouldn't let you bother you. It's just sum up all the little changes, and you get back to the level. Another way of thinking of what the stochastic integral produces is it produces a random variable. The integral, when you see the expression integral dzt, that means zt minus z0, that just means a random variable. A random variable normally distributed, mean 0, and variance t. Sometimes I write it t times epsilon when epsilon's a normal 0, 1 to remind myself there's nothing particularly mysterious about that. It's just a normally distributed random variable with mean 0 and variance t. Well, that's the easy one. That's the z. Now let's try to do some more complicated examples. Let's start with the diffusion dxt is mu dt plus sigma dz, our standard diffusion formula. What's the opposite of that? How can we solve that stochastic differential equation? Let's just plop the integral sign on both sides of that expression as you solve easy regular differential equations by just plopping an integral sign on both sides of the expression. What do you get? Integral dxt, well, that just means xt minus x0. Integral dt, if we just add up all the little differences dt, we just get capital T, the total time difference. And integral dzt, we've already met our friend integral dzt. That's zt minus z0. That's a random variable. So we have now solved a stochastic differential equation. X at time t minus its initial value is mu t plus a shock, which is normally distributed with mean 0 and variance t. Easy, huh? Let's do a little harder one. This is the one that we're going to do all the time in asset pricing. We model asset prices by thinking that the rate of return has a mean mu, a drift mu, and a variance sigma dz. So what is the finite time price? What does the price look like if we go a year ahead, 2 years ahead, 5 years ahead? To know that, this is a differential equation. We have to solve that differential equation forward and see how the price behaves many years ahead. How do we do that? Well, ignore the red stuff for the moment. Let's take the log of p first. If that's dp over p, d log p is mu minus 1/2 sigma squared dt plus sigma dz. We did that when we were doing Ito's lemma. There was a reason I did that example when we did Ito's lemma. We were going to need it right away. Now we have a diffusion for log p, and we know how to just slap an integral on both sides. Integral d log p, integral dt, integral dz. What's the integral of d log p? Well, that is, add up all the little changes. That's log p capital T minus log p 0. That's just capital T. And integral dzt you've just met. That's a shock. So now we've found that the log price is normally distributed. That's the mean of the log price after t years. And that's the variance term. That's the shock, the random part of the log price after t years. If you want to look at the price itself, exponentiate. So the price itself, or the gross rate of return, this is the rate of return from time 0 to time t. That is e to all this stuff. The rate of return is log normally distributed. That's what we call e raised to a normally distributed thing. So for example, we can take the mean. What is the mean gross rate of return? Well, that's the mean of a log normally distributed random variable. What is e of all this stuff? I use the fact that e of e to the x is e to the mean plus 1/2 sigma squared. That fact works for normally distributed random variables. And therefore, the mean of the long run rate of return is e to the mu minus 1/2 sigma squared t plus 1/2 the variance of that term, which is another 1/2 sigma squared t. The two sigma squareds cancel, and the mean is e to the mu t, as you might expect. So you've taken a geometric Brownian motion model for the rate of return and found out that the long run distribution of prices is log normally distributed. This is very important in asset pricing. We often think of the rate of return, say, of monthly returns being normally distributed, a distribution looking something like that. The log normal distribution is a good distribution for thinking about long run returns, because returns can never be negative. The log normal distribution looks something like that. Well, you take a bunch of monthly returns that look like that, and that turns into 5 and 10-year returns that look something like that. Now you know how to do it. One more slightly more complicated example. The AR1 is the one that we've been using all along to connect discrete time and continuous time. The AR1 is dxt, drifts down, and it's diffusion. You've seen the AR1 many times. What does the AR1 look like? Here I'm going to relegate the algebra to the notes. Watching me do algebra will put all of you to sleep for sure. And here's the answer, however. When we solve that equation, we have e to the minus phi t x naught plus this integral, a common set of weights times all the past shocks. This is, of course, exactly parallel to the discrete time formula, rho to the t times x naught, plus a geometrically weighted sum of all the past shocks, a geometrically weighted integral of all the past shocks. Once you've solved a stochastic differential equation, you can find the moments of the AR1 just as we found this moment here of the log normal distribution. What is the mean and variance of the AR1? This one's easy to do once you just look at the solution. What is the mean of xt? That's this term, because the mean of all those guys is 0. What is the variance of xt? Well, that term is just a constant, so it doesn't enter into variances. We have to take the variance of this integral. How do you take the variance of that integral? Well, remember, dz's only enter when they multiply themselves. dz's are uncorrelated. So the variance of that integral, the squared value of that integral, is just the squared value of the integrand, and then each of the dz squareds, which is dt. So in fact, you can find the variance from this very simple integral formula, and when you do the integral, That's the formula for the variance of an AR1. Algebra in the notes, but you can see the usefulness of the procedure. You found from the differential representation, you found how xt depends on all the past shocks, and from how xt depends on all the past shocks, you can find the mean and the variance of xt as a random variable. You may be getting all excited. I have to break some bad news to you. In general, it's not so easy. If you remember, regular differential equations weren't so easy either. Why were they not so easy? Typical differential equations, you have dxt is mu, which is also a function of xt. So when I plop an integral on both sides of here, I don't naturally have the x's on the left and the t's on the right. And you spent a whole quarter of a differential equations class figuring out how to deal with that. Things don't get any easier when sigma depends on x as well. But the concept and the idea of solving a stochastic differential equation is no harder in continuous time than it is in discrete time. So summary, what have you learned? The concept of solving a stochastic differential equation where we simply add up all the little differences. The concept of a stochastic integral, so objects like integral dx or integral dz that don't have integral dt on them, as you're used to seeing, that should now make sense to you. That just means add up all the little changes. Sometimes add up all the little changes weighted by some function of time or state variable. Another thing you learned is interpreting formulas like that, that really just means a random variable. That's a shock. In this case, integral dz is a random variable with mean 0 and variance t. And you've seen that one way to get moments, conditional means, conditional variances, is by finding full solutions and then just taking means and variances of sums and integrals of dz's, which isn't that hard. Moments is what we're all about in asset pricing. Prices today reflect expected value of dividends in the far future. Now we have a mathematical structure that we can use to start thinking about what are expected values of payoffs in the far future, what are prices, what should prices be. With that mathematical structure, we can start to go ask the real economic question, and that's what we'll do on our first lecture.